Okay, welcome. Going to start our final unit in the story of astronomy this year. Final unit that is in the ever expanding units that we've been going from, starting with the Earth's rotation, and now we're looking at the biggest picture of all, the entire universe, and what we have come to understand about its evolution. So we're going to spend quite a bit of time on this, but my job is to basically lay out for you the scientific evidence and line of reasoning that has led us to believe in this expanding universe that is finite in time. And of course, that means the observable universe is also finite in space. I say observable for reasons that we'll discuss in another lecture. But the major takeaway here, to give away the whole story, is that there is an overwhelming amount of evidence that we live in an expanding universe that started at a discrete point in time in the distant past. And I want to lay that out for you. Any one of these slides, of course, is worthy of its own lecture, but I thought it was worth to sort of like take a tour of the whole thing, get a bird's eye view, if you will, of the evidence, right? So, I mean, this is just the deep question, right? People have been wondering about, this is one of those fundamental questions that we always wonder, what, has it always been like this? Will it always be like this? And of course, as we have discovered more and more things, the human species wasn't around forever, the Earth hasn't been around forever, the sun hasn't been around forever, so what about the whole universe? Maybe that's static and unchanging. So there's this thing known as Olber's paradox. So even before any of the evidence came around, there were some there have always been some really, really smart people. And Olber came up with this idea of a paradox. If we do live in a static universe that is infinite, then that means when you look up in the night sky, in any direction, eventually there would be a star or a galaxy in that direction, in that line of sight, right? Because if it goes out forever, even if it's a random scattering of galaxies, there eventually would be one in an infinite universe. And if it's been here for an infinite amount of time, then that light would have time to get to your eye, and the night sky would not be dark, right? So this is actually an important piece of evidence that we don't live in a static and infinite universe, which is maybe kind of a nice idea. But just going out at night lets you know that cannot be so. The other problem is if you understand gravity, if you have a finite universe, right, then the gravitational attraction of all the stars and all the galaxies would eventually pull it all together. And so it could not stay that way, right? And then, when Hubble discovered the existence of these other galaxies, it is an interesting question, why is there so much empty space? We have a universe that is mostly empty space. Okay, well, here's our first piece of evidence, and it's surprising because it's completely mathematical and also was an utter disappointment to the author of the theory, and he messed up his own theory, sort of, in order to, bend over backwards to make it not so. But when Einstein originally created his general theory of relativity, right, this is our modern understanding of gravity, right, that mass warps space and time, he found that the equations that he came up with to model this fabric of space-time that was malleable by masses, it had this weird feature that it just showed that the universe was creating more space-time fabric all the time. And of course, that didn't make any sense to him. I mean, the space-time is not a dynamic thing. In his day, in his time, all the smart money was on some kind of static universe, right? There was no reason to believe that it was collapsing or expanding or any of that. And so he put an extra term in there, right? This circled term right back here is called the cosmological constant. And he stuck it in there basically to correct for an underlying expansion that the equations would show otherwise. And afterwards, because within his lifetime, Hubble made some of his observations, and it became known that the universe was expanding. And then Einstein was like, oh, I could have predicted that if I believed in my equation, right? So he called this his greatest blunder. So what did Hubble do? So in the next decade after general relativity came out, it's not that people were looking for an expansion thing. People did not necessarily believe in that. Remember, at this time, whether some Messier objects were entire other galaxies was still an open question, right? So at the same time that Edwin Hubble measured these distances to determine that there are other galaxies and that the Milky Way is only one of many galaxies, at the same time, he discovered something very strange, right? And what he discovered is that the majority, the majority of the galaxies their spectrum is shifted to the red, similar to Doppler shifted sound goes to lower frequency when it's moving away, right? So this Doppler shift exists for light as well as for sound because they're both waves. And when he plotted the distance to these distant galaxies against the amount of their shift, he got this graph right here. This is a pretty amazing thing, right? Whenever you get a nice linear graph like this, especially when it's unexpected, there's some major science afoot. So every red dot on this graph represents an entire galaxy. And on the left side, this is the velocity, it's recessional velocity. That is how fast that galaxy is moving away from us. And that comes from exactly how redshifted the light is, right? We know the spectrum of stars by looking at them in our own Milky Way. And so we look at how that spectrum has shifted, and we're going to talk about that in a separate unit. And that had been observed before, but the new feature is the x-axis here. He actually used a technique that Henry Leavitt had discovered, which we'll describe in the future, about how to measure distances in astronomy, which is a whole field in and of itself. But she discovered a way to do this, and he used her formulas, and so he got the x-axis here. But because otherwise you wouldn't be able to see this linear relationship. Now, this is it, right? This is the major piece of evidence, and this is why somebody like Einstein would look at this and say, oh my gosh, the universe is expanding. So let me walk you through that logic a little bit, right? Why would it be that something farther away would be moving faster, right? That there's this one-to-one correlation, right? The more distant objects are moving away from us faster. Even if we were the center of the universe and everything is like fleeing from us because we smell bad or something like that, they wouldn't be going faster the farther away they are, right? There has to be some underlying physical explanation that involves the fabric of space and time itself that would carry things that are farther away from us, not just make it go farther away from us, but the farther away it is, the faster it's going, right? That's the surprising thing. I guess it's surprising that they're moving away from us to start with, but the fact that they're moving even faster the farther away they're going means that this implies that the fabric of space and time itself is expanding. Here's an analogy I like to use. Imagine you're all sitting in the classroom, right, and we have these tiles on the floor, and every minute that goes by, every single tile gains 1 centimeter in both directions, right? So it gains 1 square centimeter. Well, the people in the front row, from my perspective, are only a few tiles away. And so after a few seconds, they've only moved a few centimeters away as the tiles expand, right? But the people on the back row, the farthest from me, right, there's like 10, 12, 15 tiles between the back row and myself. And so that means in the same amount of time that the front row has only moved 1 or 2 centimeters away, the back row will have moved 15 or 20 centimeters away, right? And just because of the nature of the expansion of the tiles, the things that are farther away from me get carried away faster. And that's what you're seeing here. There really was no other kind of consistent way of explaining this graph. And another bonus for that is, of course, you would see that no matter where you are. You could, my description of the expanding classroom, that would work. Any student would have the same graph from their vantage point, right? People closest to them would be moving more slowly than the people far away from them. And so this is the first estimation of the age of the universe, right? Because you can figure out exactly what the expansion, you got the slope here is telling you how fast the universe is expanding as a function of distance. And so you could run the clock backwards and figure out how long it would take for all these galaxies to collapse in on each other, right? Because if you run the clock backwards instead of expanding universe, you have a contracting universe. And even way back in Hubble's time, they got an estimation that's pretty close to the modern more accurate method that we have now. But back in Hubble's day, it was about a 15 billion year old universe. All right, so if you only have one point of data, right, the more surprising your conclusions are, the more kind of disparate pieces of evidence you want to have to support it. And Hubble is the most frequently cited one, and of course, in the popular press, you're kind of one and done, but that's never good enough for the scientific community. This one, step 3 here, the cosmic microwave background, is one that they have continually refined since the original Nobel Prize-winning work in 1964 was done by a couple of radio telescope engineers. Basically, they weren't even doing astronomy. They weren't astrophysicists at all. They were working, on telecommunication problems here on Earth. And what they discovered was a kind of a hiss, a background interference signal that was coming from all directions from outer space, right? And that's the background part of this. And the cosmic microwave, cosmic, so it's coming from the cosmos, and microwave because it's down there in the radio frequency near the microwave band. And they discovered that signal coming from all directions, and at that point, astrophysicists who were taking Hubble's work seriously were thinking about what the early days of the universe would look like, and they actually were making predictions that one would expect to have background radiation like this that dates from the earliest part of the universe in the history of the universe. And after that, we have now launched a couple of different satellite probes that look at this frequency range. And what you're looking at here, some people have called this the infant picture of the universe. And this is the cosmic microwave background. It's almost entirely uniform, but now we have experiments that are going down to the thousandths of a degree difference between one location in the sky or another. So this is a map that has been created looking in all directions from planet Earth. And all of this is indicating a uniform temperature in deep space of about 2.7 degrees Kelvin. That's the temperature of the source that would release radiation that looks like the cosmic microwave background radiation, the frequency of radiation that we see. And what you're seeing here, the slight variations in color, and there are different versions of this map depending on which satellite investigation you're looking at, these are variations down in the thousandths of a degree, right? So these are showing you some parts of the early universe that were slightly warmer and certain parts that were slightly cooler, but is remarkably homogeneous, right? Once again, this is an exaggerated differential, right? Down in the thousandths of a degree. It's basically all at the same uniform temperature. And this is precisely what people would have predicted. It would be uniform because it was small, and there would be very minor variations because eventually we know some of this is going to clump together and form galaxies, and a lot of it's going to be empty space. So there had to be some variation in a mostly uniform background, right? So you can actually draw, a straight line from this picture of the earliest distribution of energy variations down in the thousandths, the fifth or sixth decimal place of temperature, to the collection and distribution of galaxies today. Now, there are other things, right? So those are two major pieces. Another one is if the universe was created, then as we know, almost all of the elements are created in stars. And so that means if you look in the earliest portions of the universe, that means looking farthest away to look the farthest back in time, you should no longer see any heavy elements, right? And in fact, you might think that you should only see hydrogen, which is pretty close to the truth. However, some astrophysicists were thinking about just how hot the temperatures would be when the universe was in its earliest stages, in those first few seconds before it expanded enough to cool down. And they did calculate that some fusion would be able to happen. And so you could get some hydrogen fusing into helium and even some trace amounts of lithium, which is element number 3. And they can actually model those calculations based on their understanding of how hot it would have gotten as you run time backwards and heat up the universe. And they had a predicted ratio of hydrogen to helium that you would see in the earliest portions of the universe before stars had time to fuse the heavier elements. And that is when we look through the Hubble telescope, which was named after this Edwin Hubble, but that data gathered in the 1990s and 2000s, when you look really, really far back to the oldest dust clouds you can find, you have that ratio that was predicted. First of all, you don't see any heavier elements. and you see the proportions of hydrogen and helium and lithium that is consistent with the theoretical predictions. So this is another piece of evidence that the universe had a finite beginning. To say it started in a Big Bang is not a term that I would like to use because we are still in the expanding universe, right? It's not like it banged once in the past and then boom, we had a universe. We are still riding the expansion now, right? We're expanding, and we've always been expanding since the beginning. So the Big Bang has come to mean usually that initial creation of the universe, right? Where it came from, we don't know what, right? And it's been expanding ever since. So we are still in the Big Bang now, if you think about the Big Bang meaning an expansion event. So the other thing too is if you have a finite age of the universe, then when you look around and you can determine how old certain stars or galaxies are based on what we know about the fusion process in them, you shouldn't find anything older than the age of the universe, right? And that is true. Occasionally there'll be some initial estimates that'll put a really old star or maybe an ancient galaxy or some astronomical feature to be older than 14 billion years old. And then when they refine their measurements, it always comes in a little bit less than that. And so, I double checked this morning, and it's still the oldest star that we have ever seen is about 13 billion years old, and that is, of course, slightly younger than the universe. So the age of the oldest known objects is also consistent with the Big Bang idea. And then the last piece is a little bit more subtle, but we're going to talk about this, is that when you look at the distribution of galaxies, and you find, first of all, that galaxies exist and that the intervals of galaxies and then the way the galaxies themselves are arranged in tendrils and clusters, like we're clustered with Andromeda in the local group, that distribution of matter, right, that is locally clumped together in galaxies, but globally over the observable universe pretty uniform, is consistent with the cosmic microwave background and computer simulations where they run models of what would happen in a compact, highly energetic universe that then began to expand. Right? So here is basically all of this evidence to support the Big Bang theory. So it's a theory in the same sense that like evolution is a theory. This is bedrock science. You can't dispute the fact that we're in an expanding universe that had a finite beginning because there are so many different lines of observational evidence and no contradictory evidence, right? And so, we've got this shift to the red when we look at the light. We've got the abundance of the elements in the olden days, the age of the oldest known objects, the cosmic microwave background radiation itself, which is considered probably of all of these, the most definitive proof, and that is so precisely measured, and ages. That's the most accurate metric that they're using to give the age of the universe to be 13.8 billion years old. All right, lots of other things to talk about in the future. I want to talk some details about the early days and what the first few seconds here of the universe and how matter came to be from energy, but I'm going to save that for another day. Okay, thanks for listening.